This is a video for my grandparents Hugh and Laverne Headington entitled Quantum Gravity and the Architecture of the Rings of Saturn. My name is Scott Albers. What is quantum gravity? Let's start with the word gravity. On July 5th, 1687, Sir Isaac Newton published his treatise on the mathematical principles of natural philosophy. In this work he defined gravity as a force acting instantly on every other force in the universe. Isaac Newton's formulation of a gravitational force law requires that each particle with mass respond instantaneously to every other particle with mass, irrespective of the distance between them. In modern terms, Newtonian gravitation is described by the Poisson equation, according to which, when the mass distribution of a system changes, its gravitational field instantaneously adjusts. Therefore, the theory assumes the speed of gravity to be infinite. In a letter to Mr. Richard Bentley in 1692 or 1693 at the Palace of Worcester, Newton wrote the following, quote, "'Tis inconceivable that inanimate brute matter should, without the mediation of something else, which is not material, operate and affect other matter without mutual contact, as it must if gravitation in the sense of Epicurus be essential and inherent in it. And this is one reason why I desired you would not ascribe innate gravity to me. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance, through a vacuum without the mediation of anything else, by and through which their action or force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial is a question I have left to the consideration of my readers." That is to say, as Newton proposed it, the gravitational attraction of one galaxy instantly interacts with every other galaxy everywhere at the same time, in a straight line, in a colossal soup of instantaneous gravitational interaction. In his book, The Speed of Gravity, What the Experiments Say, Tom Flandern states this problem as follows. "The most amazing thing I was taught as a graduate student of celestial mechanics at Yale in the 1960s was that all gravitational interactions between bodies in all dynamical systems had to be taken as instantaneous. This seemed unacceptable on two counts. In the first place, it seemed to be a form of, quote, action at a distance, unquote. Perhaps no one has so elegantly expressed the objection to such a concept better than Isaac Newton. Quote, that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it, unquote. But mediation requires propagation, and finite bodies should be incapable of propagation at infinite speeds, since that would require infinite energy. So instantaneous gravity seemed to have an element of magic to it. The second objection was that we had all been taught that Einstein's special relativity, an experimentally well-established theory, proved that nothing could propagate in forward time at a speed greater than that of light in a vacuum. Indeed, as astronomers, we were taught to calculate orbits using instantaneous forces, then extract the position of some body along its orbit at a time of interest and calculate where that position would appear as seen from Earth by allowing for the finite propagation speed of light from there to here. It seemed incongruous to allow for the finite speed of light from the body to the Earth, but to take the effect of Earth's gravity on that same body as propagating from here to there instantaneously. Yet that was the required procedure to get the correct answer. Indeed, it is widely accepted, even if less widely known, that the speed of gravity in Newton's universal law is unconditionally infinite. This is usually not mentioned in proximity to the statement that general relativity reduces to Newtonian gravity in the low-velocity weak field limit, because of the obvious question it begs about how that can be true if the propagation speed in one model is the speed of light and in the other it is infinite. The same dilemma comes up in many guises. Why do photons from the sun travel in directions that are not parallel to the direction of Earth's gravitational acceleration for the sun? Why do total eclipses of the sun by the moon reach maximum eclipse about 40 seconds before the sun and moon's gravitational forces align? How do binary pulsars anticipate each other's future position, velocity, and acceleration faster than the light time between them would allow? How can black holes have gravity when nothing can get out because escape speed is greater than the speed of light? The notion of time as flowing in a smooth, even motion, unbroken, the same everywhere, is a very common notion of time. Newton's development of calculus used the idea of a fluxion, of change over time, and supported this notion of an infinitely divisible, unbroken, smooth, continuous flow of time and space. The changes of an object in time and space were deemed to be continuous, that is, infinitely divisible. Two things that were key in Newton's understanding of time and space were inertia and momentum. Inertia is how much something resists changes in motion. Momentum is a measure of how much motion something has. Newton was aware that his proposal for an infinitely smooth, continuous flow of time or space was not necessarily acceptable. An ancient puzzle stemming from two of the most widely known and respected Greek philosophers of the Golden Age of Greece, about 600 BC, had made very specific claims about the nature of reality. According to Parmenides of Elea, the, quote, unshaken heart of well-rounded reality, unquote, had the properties of being immobile, stationary, fixed, and absolutely one. A goddess describes the matter to him. You must needs learn all things, both the unshaken heart of well-rounded reality and the notions of mortals in which there is no genuine trustworthiness. Nonetheless, these too will you learn, how what they resolved had actually to be, all through all pervading. The traditional interpretation of Parmenides' work is that he argued that the everyday perception of reality of the physical world is mistaken, and that the reality of the world is one being, an unchanging, ungenerated, indestructible whole. Parmenides' student and friend Zeno of Elea tried to support this notion of reality being motionless. To do this, he proposed a number of paradoxes of motion, all of which tended to show that Parmenides was right. For example, argued Zeno, if we agree that Hercules is to run the distance from point A to point B, is there not a point C halfway between them, and then a point D halfway between those, and a point E halfway between that, etc.? If this is so, Hercules cannot even begin running, because there is such an infinite number of points he must cross first just to begin. Consequently, Hercules must be stationary and remain stationary from the outset, for all eternity. Newton answered these arguments with the claim that his mathematical method of calculus using fluxions was sufficient to bring the calculation to any desired degree of accuracy. Lemma 1 is where he puts this out. Quantities and the ratio of quantities, which in any finite time converge continually to equality, and before the end of that time approach nearer to each other than by any given difference, become ultimately equal. If you deny it, suppose them to be ultimately unequal, and let d be their ultimate difference. Therefore, they cannot approach nearer to equality than by that difference d, which is contrary to the supposition. But Newton did not otherwise contest the notion that at the very lowest level of reality, the flow of a straight line of space or time had problems. But gravity and time were not all that Newton thought moved in a straight line. He also thought that this was the way that light moved, in a single direct beam of light, like a radiating ray. Newton demonstrated that these rays of light were actually many colors of light. This, however, ran into trouble when, in 1801, Thomas Young demonstrated that an interference pattern, similar to the action of the tide hitting a pier, might account for the nature of light as well. To determine whether light might have the properties of a wave, he considered what ocean waves do when they strike a pylon of a pier. As the tide rolls in against each pylon of a bridge, it makes a characteristic dent in the oncoming wave. As these waves bend around the pylons of the pier, the original wave is modified considerably, particularly when there are many pylons spaced very closely to one another. When this is created, an otherwise smooth tide can become tremendously turbulent. And so Young created a similar set of barriers for light to pass through, and discovered that, rather than creating an exact shadow that rays of light would do, instead he had an interference pattern. In this fashion he demonstrated that light had wave characteristics as well as ray-like characteristics. The question became, well, which is it? And so the question of light being a particle moving a straight line, as Newton suggested, or as a wave, as Young and many others claimed, took very strong precedence. The success of Newton's approach led others to emulate Newton. In particular, James Clerk Maxwell developed his mathematical laws for electrical bodies in 1861 and 1862. It is important to notice the beautiful symmetry of electromagnetism. As a direct flowing current, an electric current is wrapped around an iron nail. This electric current creates within the iron a magnetism. On the other hand, if a set of magnets is set rotating around an otherwise neutral coil of wire, this rotation creates within the wire an electric current. It brings up the question, if a large mass is able to pull a small mass towards it across space and time, and if the motion of the smaller mass is termed as gravity, making the smaller mass fall towards the larger mass, thereby gaining momentum, then is it possible that by understanding how momentum is translated across space and time, we might somehow construct a smaller mass capable of creating a focus of gravity above itself, thereby permitting it to fall away from the larger mass? In 1897, J.J. Thomson discovered the electron. At that time, the role of the electron became well known, and a new understanding of the atomic nucleus began to develop. Quantum mechanics describes this approach to the core of the atom. In 1905, Albert Einstein developed his special theory of relativity, a fundamental assumption of which was that nothing physical may exceed the speed of light in a vacuum. This constant obviously contradicted Newton's idea of gravity propagating at an infinite speed instantly across the entire universe. Once the speed of light was taken to be propagating through space at a constant speed above which nothing physical may travel, the famous equation between mass and energy, E equals mc squared, developed from the special theory of relativity. Along with that came the idea that the location and time of something were connected to its velocity as a fraction of the speed of light. This led to a combination of Newtonian space and time into an Einsteinian space-time, which the special theory of relativity uses to indicate an event in reality. This led to the further development in 1915 of Einstein's general theory of relativity, which took the special theory of relativity and its assumptions about the speed of light and developed a new way of understanding gravity. The mathematical foundation for general relativity was tensor analysis. A vector is a two-dimensional tensor. Einstein found that by using 4 dimensions, 3 of space and 1 of time, he was able to formulate a new idea of gravity. This depended, however, on keeping the speed of light a constant, which could not be exceeded by anything physical. And general relativity does not concern itself directly with the structure of the atom. These 4 dimensions might be imagined as the 4 points of a square, 3 of space and 1 of time. One of the key points which permitted general relativity to come into being was a thought experiment which made clear that there was no difference one could determine between inertia and gravity. If one imagines being in an elevator moving up, and suddenly the top of the building is removed and the elevator continues on higher and higher, infinitely so, Einstein asked, is there any way the person inside the elevator can tell that he or she is not flat on the ground and held to the floor by the force of gravity? The answer is that it would be impossible to tell the difference. From this point on, the z-vector indicating the line of gravitational attraction is equal to inertia. This principle is called the principle of inertial and gravitational equivalence. Einstein's equivalence principle asserts the equivalence between inertial and gravitational forces of acceleration. It rests upon the fact that we cannot distinguish between the inertial forces, g forces, experienced, for example, in a rocket ship accelerating through space, and the gravitational forces experienced, for example, on the surface of the Earth, which latter are actually due to space-time accelerating through us. From this reciprocity of forces, Einstein was able to deduce the fact that gravity bends light, because gravity accelerates space-time. According to the general theory of relativity, gravity does not move in a straight line connecting two masses as Newton described it. Rather, gravity is a wave which an object having mass creates, simply by existing. The notion of time and space proposed by Newton became space-time, and the relationship between mass and energy simply became mass-energy. The question is, if this is the case, and if gravity cannot travel at an infinite speed, but the infinite speed of gravitational attraction, instantaneous attraction, is still what astronomers use to calculate the positions of stars and galaxies throughout the universe, which is it? In 1919, Theodor Kaluza proposed that if a fifth dimension was added to the analysis, which was given a value of 1 and otherwise permitted to have no effect on the equation, the resulting equations resulted in Einstein's equation for general relativity and Maxwell's equations for electrodynamics. However, this advance did not suggest any particular experiment in which the effect of this fifth dimension might be seen or understood. Also, Kaluza's work had no effect on the study of the electronic or internal structure of the atom, or quantum dynamics. In a paper published in 1921, Kaluza wrote the following, quote, "The 15 components of the curvature tensor hence split into the left-hand sides of 1. The old field equations of gravitation, 2. The basic electromagnetic equations, 3. A Poisson equation for the as yet uninterpreted G. Therein lies the first justification for our ansatz, and for the hope to recognize gravitation and electricity as manifestations of a universal field. At present, the consequences of this hypothesis cannot be estimated. Furthermore, there are other possibilities to be investigated. In any case, every ansatz which claims universal validity is threatened by the sphinx of modern physics, quantum theory. This begins the first attempt to combine all which is known about physics into a single theory." A biography of Kaluza states, "Above and beyond the epistemological components, Einstein considered Kaluza's theory a serious contender for achieving real physical unification of electromagnetism and gravitation. In this conviction, he labored on constructing theories based on Kaluza's model until 1943. Einstein's main objection to Kaluza's unifying concept seems to have been the non-existence of a fifth dimension, an objection which, owing to the continuing impossibility of empirical proof, still stands today." Another author states, quote, "Kaluza made two assumptions on this metric, that GYY equals 1, and that all other components of the metric are independent of y. Herein lies the greatest detractor to Kaluza's theory. Built into this metric is the condition that we cannot detect this fifth dimension with any experiment. This is a problem for two reasons. One is that this condition seems fairly artificial in the face of it. Secondly, and probably more importantly, the theory appears guaranteed to do nothing better than reproduce equations 1, Maxwell's equations, and 2, Maxwell's effect on Einstein. There is no Kaluza equivalent on the experiments of the experiments Einstein suggested to test general relativity, e.g. the diffusion of the light by the sun or the precession of Mercury's orbit." Another author states, "Even if one goes along with the assumption of a five-dimensional metric manifold, the postulates that this manifold have a one-parametric isometric group, and further that the magnitude of any isometric displacement be constant throughout the manifold, are logically arbitrary and can be motivated only by our physical experience." Another author writes, "Kaluza proposed that in addition to the left, right, back, forth, up, down dimensions, the universe actually has one more spatial dimension that, for some reason, no one has ever seen. If correct, this would mean that there is another independent direction in which things can move, and therefore that we need to give 4 pieces of information to specify a precise location in space, and a total of 5 pieces of information if we also specify time." Kaluza realized that the equations of Einstein's general theory of relativity could fairly easily be extended mathematically to a universe that had one more space dimension. Kaluza undertook this extension and found, naturally enough, that the higher dimensional version of general relativity not only included Einstein's original gravity equations, but, because of the extra space dimension, also had extra equations. When Kaluza studied these extra equations, he discovered something extraordinary. The extra equations were none other than the equations Maxwell had discovered in the 19th century for describing the electromagnetic field. By imagining a universe with one new space dimension, Kaluza had proposed a solution to what Einstein viewed as one of the most important problems in all physics. Kaluza had found a framework that combined Einstein's original equations of general relativity with those of Maxwell's equations of electromagnetism. Although the mathematics worked, there was, and still is, no evidence of a spatial dimension beyond the three we all know about. So was Kaluza's discovery a mere curiosity. Another author writes, over the years, problems were discovered that rendered Kaluza's theory useless. First, the theory was riddled with divergences and anomalies, which is typical of quantum gravity theories. Second, there was a much more disturbing question. Why don't we see the fifth dimension? When we shoot arrows into the air, we don't see them disappear into another dimension. Think of smoke, which slowly permeates every region of space. Since smoke is never observed to disappear into a higher dimension, physicists realized that the higher dimensions, if they exist at all, must be smaller than an atom. For the past century, mystics and mathematicians have entertained the idea of higher dimensions, but physicists scoffed at the idea, since no one has ever seen objects enter a higher dimension. In 1927, the understanding of the atomic core resulted in quantum dynamics, beginning with the famous uncertainty principle, first stated by Werner Heisenberg in the case of the electron. Quantum mechanics demonstrates that it's impossible, fundamentally impossible, for an outside observer to know simultaneously and with complete accuracy both the momentum and the position of an electron. This back-and-forth contrast between momentum and position created a completely different view of the smooth, constant flow of time which Newton had proposed as fundamental to his work. Suddenly, particle physics took on a mathematics wherein the basic parts were small, discrete amounts, or quanta. The development was quantum physics. It was a complete break with Newtonian view of space and time to that point. In 1949, Ludwig von Mises, an economist, suggested in his book Human Action, a treatise on economics, that there might be a strict analogy between economics and physics on this point. For example, if one divides the economic productivity of an economy into the realm of real goods, and contrasts that with the monetary sector, which prices these goods and services, one may make a further contrast between the sellers and the buyers, the sellers who provide their goods to buyers, and the people who save their money and thereby make it available to borrowers through the banks. Capitalism is based upon the idea that one cannot simultaneously buy the candy bar and eat it, and yet keep the money. One can choose to give up the money and own the candy bar, or save the money and not purchase the candy bar. But one cannot legally do both. Von Mises writes the following: the a priori sciences, logic, mathematics, and praxeology, aim at a knowledge unconditionally valid for all beings endowed with the logical structure of the human mind. The natural sciences aim at a cognition valid for all those beings which are not only endowed with the faculty of human reason, but with human senses. The uniformity of human logic and sensation bestows upon these branches of knowledge the character of universal validity. Such, at least, is the principle guiding the study of the physicists. Only in recent years have they begun to see the limits of their endeavors and, abandoning the excessive pretensions of older physicists, discovered the uncertainty principle. They realize today that there are unobservables whose unobservability is a matter of epistemological principle. As this might relate to the developments in the realm of general relativity, a fifth dimension might be stated by the contrast within the economy of the productive capacity of an economy and the pricing of the production which is available. The constant interplay between production and price through the intermediary of buyers versus sellers and savers versus borrowers gives some intuition of the large scope of a physical approach to the fifth dimension suggested by Kaluza to unite both realms of Maxwell's equation for electrodynamics and general relativity. The following circuit of relationships is required for the economy to exist, and by analogy, a similar circuit may exist to support the fifth dimension proposed by Kaluza. The interplay of these two opposing poles of economics, production and pricing, gives rise to a very well-known mathematics series which is found frequently in all aspects of biology. If this view of economics holds true, at some level the constant of this growth should be within view. This constant is phi equals 1.6180 ... and is found in the relationship of 1 to 1.6180 in the interplay between rectangles shown below, wherein one side is set equal to 1 and the adjoining side is set equal to 1.6180 ... An interesting association of this geometry with the activity of a wave is that if each of the sides of the square are set equal to 2, and the line connecting this square to the apex is set equal to 1.618, the ratio of the height of the apex to the plane of the square is as 1 is to 2 pi. Further work on the core of the atomic nucleus discovered that there are in reality three forces at work within the atom, these being connected fundamentally to Maxwell's equations of electromagnetism. These special forces are electromagnetism, the strong force, and the weak force. These three forces are unified in the present-day theory with chromo-electrodynamics, of which Richard Feynman is a central author. The standard model of particle physics was complete by the mid-1970s with additional work on it from that time. None of these developments, however, tie these three forces to an understanding of gravity, nor did they contest the idea of time which flowed evenly, as Newton had described it. Quantum gravity is the effort to unify these four forces together. It is sometimes referred to as the search for a theory of everything, or a unified field theory. Regarding the study of gravity, it is important to note that to this day astronomers use the Newtonian concept of gravity as a force acting instantly across distances of vast numbers of light years. No calculation involving the speed of light or limitations in the cause is considered. As Professor Grenner studied in 2004, in the second half of the 20th century, the electromagnetic and weak nuclear forces have been bound together as an electro-weak force. A powerful scheme was devised to also include the strong interaction, chromodynamics, and led to the standard model of elementary particle physics. Unification with the fourth fundamental interaction, gravitation, is the focus of much present research in classical general relativity, supergravity, superstring, and supermembrane theory, but has not yet met with success. So, what is the purpose of this video? The purpose of this video is to suggest a way which might be used to unify these four forces with experiments and observations which can be confirmed. A few points must be made by way of introduction. First, I will assume that the hunt for quantum gravity is complete if we can locate and use the fifth dimension of Kaluza. Second, I propose that this fifth dimension is the quote identity unquote of the object in question, and that this fulfills the mathematic aspect of a fourth quote space unquote dimension. By identity, quote identity unquote, I mean the dimension heretofore unstated, which allows us to say that the thing passing through time is the same thing at the end of the trip that it was at the beginning. Third, I propose that this identity has two poles or axes to it, an objective and a subjective approach to time, which results when the two are in combination with, quote, identity. This might be understood by looking at the objective and subjective notion of the identity of a note of music. As the key is struck and the string vibrates, the objective sense of the musical tone is that the sound is heard. As the key is lifted and the vibration stops, the subjective sense of the musical tone is now that it possesses an endpoint, and becomes there a subjective, rhythmic, quote, note, unquote, of music, a quarter note or a half note, a whole note, an eighth note, a 16th note, a 32nd note. This circuit, which sustains music, might be better understood in the realm of physics if we consider the two ways of looking at time as these two different versions of time construct the identity of an automobile tire. On the one hand, an automobile tire is the physical object with a particular objective context to the rest of physical reality. It sustains a car while driving down the road with enormous weight placed upon it. It is circular. It is made of a tough, hard substance able to endure great stress. but the objective sense of time for a particular tire is given by its chronologic age. This is represented by its serial number, the specific number given to it at the time of its creation, representing this objective sense of time, and the specific date and moment and batch of the tire's creation. This number gives the maker of the tire an exact understanding of precisely when, where, and what batch a tire came from in the factory. In this fashion, a recall of tires will only affect a very small number of tires. This series of serial numbers and batches of tires may be associated with, quote, an objective, unquote, measurement of time, because it considers a universal standard of time as measuring the, quote, age, unquote, of the tire. This universal, instantaneous, eternal, and objective sense of time is the sort of time which Newton considered as holding together the universe by an instantaneous version of gravitational attraction, and this as described throughout this video. The, quote, objective, unquote, understanding of time is the sort of time which Newton used to construct the theory of instantaneous gravitational attraction in 1687. On the other hand, the subjective sense of the tire is its wear and tear, the actual experience which the tire has been through, the roads, the weather, the people who have made use of it, the travels, the specific set of events which have worn it down to a particular point at any point along the existence of the tire. The subjective sense of time for a particular tire is given by its wear and tear. This is represented by its tread, the depth of the tread indicating an enormous spectrum of possible use, from great to minimal, representing the, quote, subjective, unquote, sense of time and the particular wear and tear of this particular automobile tire. This is usually demonstrated by placing a penny in the tread of the tire. If one can see the head of Lincoln, it is time to get a new tire. This particular, temporal, limited, and subjective sense of time is the sort of time which Einstein considered as holding together the universe by a gravitational attraction limited by the speed of light, as described throughout this video. The, quote, subjective, unquote, understanding of time is the sort of time which Einstein used to construct his general theory of relativity. These two aspects of, quote, identity, unquote, understood as the objective and subjective understandings of time, combine as two different poles of Kaluza's fifth dimension to create a back-and-forth contest between them, which states the identity of a thing. This immediate, instantaneous, back-and-forth contest between the opposing ends of the fifth dimension operates just as the x and y and z dimensions of the axis of our physical experience have positive and negative sides to them. So, with identity, we see the same constant juxtaposition of these two aspects of time. As this relates to experiments which might be created to demonstrate the nature and the inquiries which might be made of a physical fifth dimension, we might note that our lives themselves are constantly shaped and surrounded by our own identity and the identity of everything around us. Our inability to detect or measure or understand this identity, or otherwise how this fifth dimension of identity might affect us, comes about because we ourselves are part of these two notions of time. As identity relates to the other four dimensions, the fifth dimension of identity states a dichotomy which operates outside and independently of the other four dimensions, albeit it is affected by and interacts with them. Generally, however, it is unnoticed because it is hiding in plain sight. However, in the case of Saturn, the planet Saturn, the matter is quite different given the speed of Saturn's spin and the oblate shape of Saturn's sphere, the squashed shape of Saturn itself. I now want to describe how experiments might be conducted on the fifth dimension, assuming that the fifth dimension or of identity is acceptable for the purposes which Kaluza had in mind. First, the objective sense of time as Newton would understand it might be represented as a single straight line from the Sun to planet Saturn, simply named line SP. As we have seen, astronomers continue to use this idea of an instantaneous gravitational attraction in calculating the position of planets and galaxies. If we take this as the objective aspect of identity of the fifth dimension in this context, we are simply stating what is already known and used by astronomers as a routine and a fundamental part of their work. The objective understanding of time would permit an instantaneous association of vast distances by gravity as is presently done by astronomers. Second, the subjective notion of time, limited and bounded by the speed of light, thereby stating gravity as a curvature or wave of space-time, might be represented as the tangent of Saturn to its own orbit as it travels around the Sun. This represents time as Einstein would understand it. A single straight line intersecting the objective line of time will represent the subjective time of the fifth dimension proposed. As we have seen, this notion of time is one astronomers use as well as the objective understanding, and the speed of light is also used to calculate the position of stars and galaxies. If we take this intersecting line at 90-degree axis to the objective line SP, we simply state the subjective aspect of identity of the fifth dimension in this context. Again, we are simply stating what is already known and used by astronomers as a routine and a fundamental part of their work. To craft experiments on these two poles of identity, let us simply imagine the situation between the Sun and Saturn by first imagining that their axes are parallel to one another. Second, imagining that their equators lie in the same plane. Third, that the equator of Saturn has the same geographic locations as Earth. And finally, that these axes are perpendicular to the plane of Saturn's equator. In this case, the equator of Saturn lies in the same plane as the Sun, and the Galapagos Islands of Saturn lie on the equator of Saturn. Let us further imagine that there is a beautiful bay in these islands of Saturn, and that a boulder in the bay is washed by the waves as it makes a rotation around its polar axis for a single day in the life of Saturn. That is to say, once each day this boulder lies directly beneath the Sun. As we would mathematize the identity of Saturn under an objective form of time, Newton's understanding of time could be graphed as the boulder spinning around the axis of Saturn as measured from line SP, the objective line of time described for Newton, and this would thereby describe a sine wave. In other words, looking down on the planets with their axes pointed beneath us, towards us, we have the following. In this way, we may measure the objective chronologic time as a measurement of the boulder of the Galapagos Islands of Saturn as it moves at a distance from the line SP. As it moves along the equator, and as we view it from the top, it goes like this. If this is done, we can see that the rotation of the boulder around the planet may be associated with a sine curve. The boulder going on the rotation of Saturn may be considered to be the objective sense of time in this context. If we were to turn this into a subjective sort of time, we might consider an airplane flying directly above the boulder, thereby, quote, experiencing, unquote, the rotation of Saturn as a function of its own gas tank. Assuming that the gas tank has enough gas to make a single trip around the equator of Saturn, as the gas runs down, the subjective experience of the boulder is stated by the airplane moving through the air. In this fashion, we now have an idea of the limited, concrete, individual notion of time, which Einstein might suggest. We would still get a sine curve, but if we were to take it as a coefficient of the amount of gas in the gas tank, starting out with 1 over 1, and then halfway around 1 over 2, and then completing the trip at 0 over 1, we would have a dampening sine curve. But there's no need to do this, because the objective sense of time is complete in and of itself. It does not need the personal experience of anything as to what it does. The objective sense of time is amply stated as the boulder spins around and around on its axis, never affected by anything. It is instantaneous and it is eternal. There is, however, a subjective way of looking at the boulder, one which states a subjective concept of time, just like there is a second way of looking at time associated with an automobile tire, by considering the wear and tear which it has experienced. Let's start with a measurement of time in a subjective fashion vis-a-vis the tire. Because the matter is no longer eternal or independent of anything else, we would need to graph, number 1, the relationship of the tire to the road, number 2, the relationship of the road to the tire, and number 3, the interaction of these two relationships upon each other. As these relate to the idea of the boulder spinning around the equator of Saturn, we must now measure what we might refer to as the, quote, tire to the road aspect of it. The relationship of the tire to the road in this case is simply the subjective experience of the boulder as measured against the line running tangent to the orbit, intersecting the line SP at a 90-degree angle. In this case, the boulder is understood as a matter of subjective time to be connecting to a line perpendicular to the objective line of SP. This would be understood as the subjective concept of time proposed by Einstein in his general theory of relativity. In this case, beginning at exactly the same time and spot as before, we now have a cosine curve rather than a sine curve. This creates a graph of the subjective experience of being a tire on the road, or in the case of Saturn, a boulder being measured from the same spot before, but against a different line, being measured against the orbital line running 90 degrees from the objective radius graph previously. But what of the analogous effect which we might graph for the boulder of the subjective effect of the road upon the tire? The road upon the tire, if we were to graph this picture, the graph of a subjective element of this same boulder as it moves around the rotation of planet Saturn, we might associate the rotation not with the boulder, but rather with the flight of the airplane unattached to the planet, flying at all times directly above the boulder. In this case, the amount of fuel in the tank might be given as sufficient to make a single trip around the equator of Saturn, but without the assistance of Saturn beneath it itself. Because we seek to add a subjective element to the equation, let us see in the fraction of fuel left in the fuel tank a measurement of the subjectivity of this motion around the axis of Saturn. As the fuel tank at the beginning of the flight is completely full, we would begin the cosine curve with the fraction 1 over 1. By the time the trip is half over, half the tank of the fuel would remain, half the fuel tank would remain, and the cosine would be multiplied by 1/2. By the time the trip is 3/4 of the way complete, 1/4 of the fuel in the fuel tank would remain, and the cosine curve would be multiplied times 1/4. As the trip is completed, one rotation of Saturn later, the fuel tank is empty, and the cosine curve at this point would be multiplied by 0. In this case, we have described a damping cosine curve whereby the boulder is given both a subjective relationship to the orbital line, and the orbital line is given a subjective relationship to the boulder vis-a-vis the experience of the fuel slowly emptying from the fuel tank. However, this would imply that the subjective concept of time is not itself infinite. So the fuel tank must be imagined as ending the trip with half the tank left, which then magically refills to 100% for the next trip. In this case, the fuel tank of the airplane may be imagined as taking 1/2 the tank to circle the planet. It is a magical tank and never ends. There will always be a half a tank of gas ready to go every time we pass the origin of the cosine curve originally. Thus, the cosine curve damps by 1/2 rather than completely. How would we graph the interaction of these two aspects above, the subjective experience of the tire to road and the road to the tire? To answer this, let us imagine that the subjective motion of the damping cosine curve is made in the opposite direction of the boulder. If the subjective notion of the trip ends with its intersection of the boulder itself, in this case we have a damping cosine curve of two periods, the first being a cosine curve as it approaches the boulder halfway around the other side of Saturn, and the second lesser cosine curve as it approaches the original position of the two. In this case, we have stated the identity of Saturn from both its objective and its subjective statements of identity at the same time. The equation for the combination of these two approaches to time, subjective and objective, is as follows. This graph gives us the beginnings of an understanding of the identity of Saturn, otherwise known as Saturn's fifth dimension. Our exploration of the architecture of the rings of Saturn begins with a study of the various curves and points which occur along this graph. It is important to mention that this identity wave, as applied to any sphere, would not be evident in the space around the sphere. If the planet was stationary, the same graph could be derived from any angle as long as the measurements were taken on the largest circle of that particular angle. In other words, an identity wave for a planet that was perfectly spherical would never be in evidence, because the two forms of time are so complementary and necessary to one another that the very perfection of the sphere would balance each of them against one another. Such an identity wave would be indistinguishable in a perfect sphere because the polar radius would equal the equatorial radius, and each of the measurements of either objective time or subjective time would be exactly the same no matter the angle considered from whence to take the measurements. In the case of Saturn, however, because of the spin of Saturn, the identity wave as indicating the identity of Saturn and the existence of its fifth dimension as proposed provides a dramatic difference between the equatorial radius and the polar radius. Consequently, the peaks and troughs of this identity wave are clearly visible as gaps in the rings of Saturn. Thus, the architecture of the rings of Saturn display the work of the fifth dimension vis-a-vis a display of the identity wave proposed. The relationship is exact. The concept of identity, however, and the idea of a fifth dimension is useful in many other branches of science, and most importantly, but certainly not exclusively, macroeconomics. Indeed, it is not too much to say that an understanding of the mechanisms of identity in other fields may lay a fertile groundwork for ideas of experimentation and discovery as applied to the architecture of the rings of Saturn. Consequently, the rest of this video will summarize the most important aspects of macroeconomics post-1949, with other developments as well, which lead to a better understanding of the fifth dimension specifically and the science of identity generally. In 1962, Arthur Oken established that a direct ratio of 1 to 3 governed the relationship between percent changes in the rate of employment and percent changes in real gross national product. In other words, for every 3% increase of real gross national product in the United States, the rate of employment was raised by 1%. This ratio has been one of the few macroeconomic constants which may be measured across economies. This is very close to ideal measurement given by the dynamic proposed above. Oken wrote, quote, "The basic technique I am reporting consists of a leap from the unemployment rate to potential output rather than a series of steps involving the several underlying factors which might impact on potential output. Strictly speaking, the leap requires the assumption that whatever the influence of slack economic activity on average hours, labor force participation, and man-hour productivity, the magnitudes of all these effects are related to the unemployment rate. With this assumption, the unemployment rate can be viewed as a proxy variable for all the ways in which output is affected by idle resources. The measurement of potential output, then, is simplified into an estimate of how much output is depressed by unemployment in excess of 4%. The answer I have to offer is simple and direct. In the post-war period, on the average, each extra percentage point in the unemployment rate above 4% has been associated with about a 3% decrement in real gross national product. My own subjectively weighted average of the relevant coefficients is 3.2, yielding the following estimate of potential. In 1975, the idea of a musical circuit was developed to understand the relationship between continuous and discrete motion. The idea was of a space-time that was discrete and continuous, that is, a piano playing music, note by note, which eventually made up an entire piece composed of individual notes. First, the key of the piano was struck, which made the string vibrate, and this resulted in the sound of a particular tone of music coming from the piano. And then the key was lifted, and the string's vibration stopped, which gave an end point of the sound itself, thereby giving a rhythmic or time element to the sound, a time value. This made it a note of music, rather than simply continuing on as unmusical sound. In this way, Zeno's paradox, which suggested that motion had to be understood as something not infinitely divisible, was answered with a model for motion in discrete parts, notes in a piece of music, one after the other in solid chunks of moments or notes, all of which resulted in a voyage from the beginning of the piece, or where Hercules begins his race at point A, to the end of the piece of music, where Hercules finally reaches the end of his race at point B. The idea was that the identity of Hercules was what made the voyage. The simple singleness of the image of Hercules like a person in a film, each picture being discrete and yet adding to the view of Hercules running a race. The first use of this idea was to calculate the identity of Saturn. If a smaller object, which was held together entirely by its own gravity, approached Saturn, it was reasoned that the internal core of Saturn would be affected by this outside force of gravity, and that it would set up within Saturn a large set of waves, each one pulsing through Saturn, and eventually resulting in a flat wave at the position of an equilateral triangle with one angle at the spot on Saturn nearest to the approaching satellite. It stood to reason that as the smaller object moved closer to Saturn, it would lose its own identity to that of Saturn's as soon as it reached the image of the flat wave that was extended out into space. At the time, it was not known what a, quote, image, unquote, was, but it seemed reasonable to think that so much identity turbulence within the interior of Saturn would be reflected into the space outside Saturn as a mirror reflects light. This would occur at 2.5 radians of the larger planet, as measured from the center of the larger planet. This was very close to the Roche limit, which is calculated as being virtually the same, but according to much different calculations. But the idea was rejected because it was implied that there would be enormous turbulence of the waves within the rings of Saturn, and in 1975 the rings of Saturn were thought to be flat and motionless. If this model predicts such turbulence, it was believed that this very turbulence would disperse the rings themselves. In 1985, National Geographic magazine reported upon discoveries within the rings of Saturn as follows, quote, "Astronomers have been faring a bit better with resolving the riddles of Saturn's main rings. When the Voyagers began to photograph these rings labeled A, B, C rings from the outside in, scientists found far more structure than they imagined. Instead of a few rings separated by the gaps visible by telescope from the Earth, Voyager found thousands of grooves, bands, and ringlets within the rings. Moreover, each main ring seemed to be ruled by different and distinctive mechanisms. Despite intensive study over the past 5 years, the rings still confound. But we do know for certain now that the ice particles that compose the rings range in size from a pebble to a boulder. Also, we see the rings, which extend for hundreds of thousands of kilometers, are extremely thin, in places only 10 meters. Quote, "If you built a model of the rings to scale," unquote, says JPL astronomer Rich Terrell, quote, "and the rings were the thickness of a piece of paper, the whole system would be 4 football fields across," unquote. But we do not understand, for instance, why the A ring appears relatively smooth, and the B ring seems to be a jumble. The most stimulating discovery, however, is the great waves within the rings. Much as Earth's tides are raised by tugs from the moon, these rings' waves are triggered as tidal tugs from Saturn's many small inner satellites. Take energy out of the rings. The waves come in two varieties. Those called density waves spiral through the rings, as if along the grooves of a record. Like passing a bad check, they transfer outward the energy deficit caused by their triggering moon. Others, called corrugated or bending waves, ripple through the planet, toward the planet, as if through a puddle. They make phenomenal mountains half a kilometer high as they move across the thin, flat ring, says Terrell. Although these waves are caused by an energy loss, the disturbances they provoke create countless energy-releasing collisions between ring particles. As a result, the rings are so dynamic that some scientists are now questioning the long-held belief that the rings are almost as old as the solar system itself. Most astronomers assume the rings are made up of leftover debris from the era of accretion, which Saturn's tidal gravity kept from coalescing into a moon. However, now the rings are so energized that theorists are asking what anchors them. Gravitation theory says that the inner ring particles should be losing energy to the outer ring particles. If so, why have they not all spiraled into Saturn? Conversely, what has kept the more energized outer particles from spreading out into ever more tenuous orbits and vanishing? Voyager did find small shepherd moons that apparently absorbed some of this outward thrust, anchoring the outward edges of the rings. But all the energy these shepherd moons would have absorbed over the eons should have pushed the satellites themselves much farther from Saturn than they are. What anchors these shepherding moons? Astronomers cannot say for sure, but Caltech theorist Peter Goldreich suggests that since the rings have not dissipated, they may not have been around very long. "I used to think the rings were very ancient," said Goldreich, "but now it appears they could be only a 50th to 100th as old as the solar system. If the rings are young, they probably are a piece of a small Saturnian moon that was hit by a big comet. Scientists by nature hate to invoke such catastrophic explanations. However, the more we see of other worlds, and indeed the better we see our own, the more we must admit that catastrophes not only occur but should also be expected." The circuit developed in 1975 offered the possibility of accommodating both the infinite subdivision which Zeno proposed to stop motion, and also of accommodating a set finite number of points which would permit motion to occur because it contested Zeno's claim of an infinite subdivision directly. If a fugue by Johann Sebastian Bach takes 5 minutes to play, those 5 minutes of time can be subdivided infinitely, as Zeno suggests, and with that suggestion, Zeno would argue that the piece cannot be played at all. On the other hand, the fugue has a finite number of notes, and this number can be divided by 2, and then by 2 again, and so on, to a finite number of divisions. The very finiteness of this division argues against Zeno's paradox and its barrier to motion because, taken from this particular point of view, the fugue cannot be infinitely subdivided. This is more obvious with a note of music than it would be, for example, of a motion of Achilles on his race. In the matter of Achilles, each motion of his body, each hand gesture, each foot placement, etc. of Achilles is not unlike the motion of the race itself, a physical thing passing through time and space. Under Zeno's paradox, each of these motions invites additional infinite subdivisions, and the argument that motion is impossible continues. A piece of music, however, contains both the possibility of an infinite subdivision of time, which is present within the span of 5 minutes, arbitrarily taken up to play the fugue, and a finite number of notes, which cannot be infinitely subdivided. A whole note, which is to be played at the beginning of the third measure, cannot be subdivided into 2 half notes, because both of those 2 half notes are fundamentally different notes than the whole note specified. The question arose, is this circuit of any use in realms outside music and an approach to Zeno's paradox? The first thing to notice about this circuit is on the right-hand side we have the piano creating a sound, and on the left hand we have a piano ending the sound, thereby permitting it to create a note. If one sees logical principles as setting up these dichotomies, a proof of Zeno's paradox is possible. For example, if we agree that, quote, a thing cannot be and not be at the same time in the same way, unquote, then being can be put on the right side of the circuit and not being can be put on the left. The vertical axis might stand for the proposition that, quote, a thing which exists must have as its opposite something which also exists. A supporting example would be a blackboard which has a single white dot on it. The blackness of the blackboard makes the distinction of the white dot easy to see. If the dot is made larger, the situation does not change. However, if the entire blackboard is covered with white chalk, indicating that the white dot has become so large that it covers the entire blackboard, the dot has become impossible to see. It no longer exists because it no longer has an opposite. The blackness of the blackboard to distinguish the dot is essential to the dot's existence itself. It no longer exists once it becomes that overwhelming because it no longer has an opposite from which its existence can be confirmed. In this way, the dichotomy between point and space, which Zeno sets up at the beginning of his argument against motion, is correct. As long as a point exists to subdivide the line, there will always be space left to subdivide. On this point, Zeno is absolutely correct. But the possibility of a view of the continuum as a musical score, rather than as a set collection of points, or an infinite collection of points, offers an alternative to explore. Ultimately, dichotomies were located in the following areas. Beginning with music and Zeno's arguments, the history of Western Europe suggests the dichotomy of an aristocratic sovereign contending against a bourgeois peasantry. The behavior of an electron is a contest between the mass energy or momentum of the electron contending against its space-time or position. The interaction between buyers and sellers in an economy is opposed to the financial positions of savers and borrowers. The self and its opposite are both things which are real, yet these contend against the negation of the self and the context of the self, which are always fluctuating. The competition between your hand and my hand in gin rummy, each one striving to win, is completely unlike the draw pile and the throwaway pile, neither of which can win. The ability to see witnesses in court give relevant and irrelevant evidence is unlike the out-of-court testimony presented by hearsay or by not hearsay, in which people recite what they heard outside of court. The individual sets which are proposed as normal sets in set theory are completely unlike the sets which aspire to include all the members of such sets. And in this paper I argue that if the x and y dimensions of space are distinguished from the z dimension and time, a fifth dimension may be advanced which contains both Newton's instantaneous gravity as an objective form of time, and the gravity of general relativity and its more subjective form of time. The mathematical result of this contest is seen throughout the behavior of the rings of Saturn. These various dichotomies may be used to suggest analogies as to the way in which naturally occurring forces contend against one another in predictable ways. Comparing these dichotomies to one another also can be used to suggest the things which bring them together, or unify otherwise competing elements. In this video, we are looking to macroeconomics for insight as to the, quote, identity, unquote, of an economy. If it is Achilles' identity which joins together various frames of his race from point A to point B, then our hope is to gain from the study of macroeconomics some insight as to the nature of, quote, identity, unquote, generally. In turn, this idea of identity might be understood as the fifth dimension suggested by Kaluza in his work on general relativity. One of the fundamental structures of the study of macroeconomics is the notion of gross national product. This is defined as the sum total of all goods and services produced in a single year. Figures for the gross national product of the United States begin in the late 1860s. If we relate one year's production to another, a wide variety of approaches can be mentioned. However, if we see this production as the generation of an actual identity for the United States for a particular period, we might consider how this comparison might best be made. Music is a form of art in which different wavelengths of sound are placed against one another in an effort to attract the interest and emotion of the people affected by the art. Some of these juxtapositions of two notes, their harmonies, are instantly pleasing to the ear, and this lack of irritation is referred to as the tones being consonant. On the other hand, some harmonic intervals are very grating and unpleasant, and these are referred to as being dissonant. It is well known that two people singing exactly the same note, harmonically referred to as a unison, has no dissonance in it at all. It is also well known that a person singing an octave higher than a second person is, again, a harmony which is very pleasing and consonant. The octave is a musical harmony without dissonance. For the purposes of the development of the ideas in this video, it became extremely important to graph harmonies of music in a fashion which could be used as a template for work elsewhere. In 1993, William Stitharis published his article Relating Tuning and Timbre in the Scientific Journal of Experimental Musical Instruments. In this article, he described the construction of a graph to indicate dissonance, or lack of dissonance, between different intervals of music. Quote, to explain perceptions of musical intervals, Plomp and Levelt note that most traditional musical tones have a spectrum consisting of a root or fundamental frequency and a series of sine wave partials that occur at integer multiples of the fundamental. Figure 2 depicts one such timbre. If this timbre is sounded at various intervals, the dissonance of the intervals can be calculated by adding up all of the dissonances between all pairs of partials. Carrying out this calculation for a range of intervals leads to the dissonance curve. For example, the dissonance curve formed by the timbre of figure 2 is shown in figure 3. Observe that this curve contains major dips at many of the intervals of the 12-tone equal-tempered scale. The most consonant interval is the unison, followed closely by the octave. Next is the fifth, followed by the fourth, the major third, the major sixth, and the minor third. These agree with standard musical usage and experience. Looking at the data more closely shows that the minima do not occur at exactly the scale steps of the 12-tone equal-tempered scale. Rather, they occur at nearby simple ratios 1 to 1, 2 to 1, 3 to 2, 4 to 3, 5 to 4, and 5 to 3 respectively, which are exactly the locations of notes in the justly intoned scales. Thus, an argument based on tonal consonants is consistent with the use of just intonation, scales based on intervals with simple integer ratios, at least for harmonic timbres. In 2007, Edward Notek evaluated the trend lines of Oken's law in the United States and established the data set necessary to determine that a ratio of 1 to pi governed Oken's law in the United States. In 2012, Andrew and Scott Albers established that the economy of the United States is governed by octaves of real gross national product ratios of 14 years apiece. And the full list of gross national product ratios are examined. Over the course of this history, a distinct octave relationship occurs in 14-year intervals. These 14-year intervals give rise to a damping cosine curve with a period of 56 years. As noted in the article, quote, "We noted in the above that the 56-year period, 14 times 4 equals 56, between peaks at 1861 through 1917, suggests the possibility that similar periods might connect other peak points of inflation. With a 14-year span, blue rectangles below is drawn around the years 1805, 1861, 1917, and 1973, each of which is separated by periods of 56 years. Virtually all inflationary peaks are contained in a single model. A damping cosine curve may be constructed as follows to fit this pattern. In turn, this is unified by a 56-year circuit of time of political change. Placing this sine curve in blue as superimposed upon the red damping cosine curve, we have the following. As maintained by various political developments over time, the ratio of 1 to 1.618 develops in the United States economy. Quote, "We then place the U.S. real GNP figures given in dataset 2 / U.S. real GNP, unquote, in a 56-year circuit, with the 4 14-year quarter cycles indicated in blue to create the spiral below. The center of the spiral, beginning at axis 9 equals 1869, represents the real gross national product for that year of $23.10 billion in 1958 prices. The gross national product for the subsequent years in real terms are given along each axis, respectively, with each circle of circumference representing $10 billion of real gross national product in 1958 prices. The sum total by way of relationships of a 14-year basis was 1.618. Moreover, one of the key mathematic ratios of Oken's law, as found in the United States, is shown to be a 1 to pi ratio. That is, for every pi units of increase in the real gross national product of the United States, unemployment falls by 1 point.